Hello, this is Mr. Underkoffler, and today we're going to be looking at the guided notes on rotations on the coordinate plane. This is our third lesson on transformations. Follow along with me. It says a rotation is a transformation in which a figure is turned around a fixed point. This point is called the center of rotation. Rotations are called turns. Since a rotated image and its original figure have the same size and shape, they are congruent. Rotations can be clockwise or they can be counterclockwise. And since we live in an age with digital clocks all over the place, whether it's on our phone or smartwatch or whatever, I wanted to show you some analog drawings here of what clockwise means and counterclockwise for those of you who might not be as familiar with that. There it is. All right. Let's take a look at what happens when there's a 90 degrees clockwise rotation. So, first example here. What used to go up will now go to the right. So follow along with this. This ray used to point up, but after a 90-degree rotation clockwise, now it would go to the right. So that's what I'm trying to say. What used to go up will now go to the right. Let's look at this next one. What used to go to the right after a 90-degree rotation will now go down. And I'm not going to highlight all of these. You can follow along with me. What used to go down will now go left after a 90-degree rotation. And the last one, what used to go left, this black ray, once I rotate it 90 degrees clockwise, then it will go up. So that's what a 90 degrees rotation will do. A 90 degrees clockwise rotation will do. Feel free to look at this back at this part of the guided notes to assist you on any problem that we will end up doing on this packet of guided notes. Now, let's look at what happens when there is a 180 degrees clockwise rotation. I'll be honest with you, this one is much easier for kids to understand. You'll see why very soon. What used to go up will now go down after a 180 degrees rotation. What used to go to the right, as you see here in black, once I do 180 degrees, will now go to the left. Continuing on, what used to go down here in black, once I rotate 180 degrees, now it'll go up. And what used to go left, once I rotate 180 degrees, will now go to the right. So basically, do you see what I see? When you do a 180 degree rotation, everything goes in the opposite direction from what it used to. So I find that to be much easier for students to understand than the 90 degree rotations. But I wanted to go over both of these in your guided notes so that way you have this as a point of reference to help you on the other problems that we're going to be jumping into. Now let's go ahead and take a look at an image on the coordinate plane, and we're going to start with the original figure over here on the left. Now, if you read the little statement here, it says the images below show clockwise rotations of a figure with a center of rotation at point A. That means point A is going to stay where it was, and we're going to rotate the image about that point A. So this kind of looks like a flag, and let me show you how what I was talking about earlier can be applied to this drawing of the flag being rotated in several different ways. For example, the flag used to be 3 units tall, but once I rotate it 90 degrees clockwise, well now, instead of being 3 units tall, it's 3 units to the right. That's what I was trying to tell you guys earlier up here. What used to go up will now go to the right when there's a 90 degrees clockwise rotation. So that's what happens with the 90 degrees clockwise rotation. Likewise, the flag used to be 2 units wide. Well, now that's going 2 units down. Again, that's the idea of what happens with a clockwise rotation. All right, let's look at the 90 degree clockwise rotation. Now let's look at 180 degrees rotation. Instead of going up 3, it's now going down 3 from point A. And for the 270 degree rotation, which can be a little tricky to understand, here's what you need to know in parentheses. A 270 degrees clockwise rotation is the exact same thing as a 90 degrees counterclockwise rotation. So instead of rotating to the right 90 degrees, we can treat it as rotating to the left 90 degrees for counterclockwise. So instead of going up 3 units, we are going to the left 3 units. And that's a set of examples with a diagram that looks kind of like a flag on the coordinate plane to show you how different rotations will work. All right, moving on. Let's turn the page and let's do 2 problems not on the coordinate plane. Problem number 1, draw the figure. As you see here, this quadrilateral with point M, draw the figure after a 90 degrees clockwise rotation. And then problem number 2, you're going to draw the figure that we have here, another quadrilateral. This time it looks like a trapezoid, a little diagonal there, with point J, and we have to draw it after a 180 degrees clockwise rotation about point J. Try these 2 problems on your own if at all possible. So hit pause on the video, and then when you're ready, when you've done 1 and 2, then hit play to see how you did. All right, I hope you did these 2 problems on your own. So let me try to, as I explain it, take it back to what I was showing you on the first page. With a 90 degrees clockwise rotation, this is what we are looking at. And right here, what used to go right will now go down. So if I apply that to the problem that I was looking at here, obviously the top of this quadrilateral used to go left and right. So instead of going left and right, when I rotate it 90 degrees, it will go up and down. And so you can see that part here that used to be at the top, now it's over here on the right going up and down. So that's how a 90 degrees rotation works. Now, if you found that to be tricky, especially without having a coordinate plane, one thing I've had some students do in the years past, they'll actually take their guided notes paper, pretend this thing I just selected is the paper, they'll actually rotate it 90 degrees. Unfortunately, my highlighting didn't rotate with it, but you see what I mean. And oh, look, and then they quickly rotate it back to put it back where it was. And then they try to draw what they just saw. And they might continue doing that back and forth, rotating it and putting it back, rotating it, putting it back. So if that little trick helps you, especially on problems like 1 and 2, then feel free to do that. I mean, there's nothing wrong with that. Work smarter, not harder. If that's working smarter for you, that's fine. All right, problem number 2, draw the figure after 180 degrees clockwise rotation. By the way, I didn't even have to put the word clockwise. Going 180 degrees clockwise and going 180 degrees counterclockwise put you at the exact same place. Everything will go opposite of what it used to. So, for example, this little line segment up here that connects to J, instead of being at the top and going right and left, we're going, I guess, to the left from J. Now it's going to be at the bottom and going to the right from J. So that's what I mean by 180 degrees. Everything goes opposite of what it used to. This part right here used to go down and it was over on the left. Well, now it's going up and it's over here on the right. So that's how a 180 degrees rotation works. Everything will be completely opposite of where it used to be. Instead of going left, we're going right. Instead of going up, we're going down. That's how 180 degrees rotations work. All right, let's actually move to some coordinate plane examples. Now, problem number 3 is already 100% typed up for you in your guided notes, but let's talk through it. It says quadrilateral WXYZ has vertices, and then they tell you what they are. You can read it to yourself. It says graph the figure and its image after a clockwise rotation of 180 degrees about vertex X. Then give the coordinates of the vertices for quadrilateral W prime, X prime, Y prime, Z prime. All right, so this was like 3 things that the directions tell us to do. The first thing it says is graph the figure. So step 1, graph the figure. All right, and you can see I did that over here. Here's W, here's X, here's Y, here's Z. They are the same locations that the ordered pairs describe up here on the opening sentence. So that's step 1. Step 2. Now we have to start doing with graphing the image. Now we're going to take this piece by piece. Remember how it said it's a 180 degree clockwise rotation about vertex X. Now that means X is the point of rotation. That's the center of rotation. Everything is going to be rotated around that point. So 180 degrees. Remember, everything goes completely opposite from how it used to be. So, for example, and this is what step 2 is saying, since vertex X is our center of rotation, we're going to count the number of spaces from X to W. Here, let me show you that. From X to W, I would count, let me choose the blue color here. I would count 2 spaces left and 1 space down. And you can see I have that typed up for you. 2 to the left, 1 space down. But after a 180 degree rotation, instead of going left and then down, it would go right and then up, as you can see. And so that's where W prime, the new vertex of W called W prime, is going to be after the 180 degree rotation. And you can see I have that typed up for you here. To graph vertex W prime after 180 degree clockwise rotation, you would go 2 to the right and 1 up. So instead of going 2 to the left, we're going 2 to the right. Instead of going 1 down from X, we're going 1 up from X. Everything goes in opposite directions when you do a 180 degree rotation, as the first page of your guided notes explained to you. So that's steps 1 and 2. Let's keep going. Step 3, graph the remaining vertices, which I guess would be what? Y prime and Z prime. After a 180 degree rotation is about vertex X. For example, to get from X to Y, you would go 1 space to the right and 3 down. Here, I'll show you that visually here. To get from X to Y, I'd go 1 to the right and then 3 down. So I need to do that now in the complete opposite directions. Instead of going 1 to the right, I would go 1 to the left. Instead of going 3 down, I'm going to go 3 up from X to get to Y prime. And that's what it says right here. Likewise, instead of going 3 spaces down to get from X to Z, here I'll show you that, 3 spaces down to get from X to Z, pretend that's straight, I'm going to go 3 spaces up to get from X prime to Z prime. That's what 180 degree rotations do. Everything goes in the opposite direction. All right, let me erase these things I quickly was drawing. All right, and then connect the vertices to form the new quadrilateral W prime, Z prime, or sorry, W prime, X prime, Y prime, Z prime. And that's what I did here in green. And that gives you the new image after a 180 degree rotation. Are we done? No, because remember the directions in the last sentence said, give the coordinates for the new quadrilateral with all the primes. So we need to give those coordinates, is what it said. So that's step 4. You just figure out what these coordinates are. Now here's the cool thing. Remember how X was the point of rotation, the center of rotation? So X prime and X, they are the exact same dot, so they're going to be the exact same down here, no big deal. But then you'd have to figure out, the coordinates for W prime and Y prime and Z prime, write them out, and you have done what this problem number 3, had asked you to do. All right, problem number 4. If you felt that number 3 was a good enough explanation and an example for you to now do number 4 on your own, then please feel free to hit pause on the video and do number 4 on your own. However, if you're not quite feeling that you could do number 4 successfully on your own, you would rather listen to me guide you through, that's fine as well. We will definitely have some independent practice problems on the last couple pages, so it's okay if you want me to lead you through this. Let me go ahead and do that. If you don't want to hear me lead you through, then hit pause right now and do this on your own. All right, here we go. Problem number 4. Triangle ABC has vertices A and B and C. You can read what they are. Graph the figure and its image after a clockwise rotation of 90 degrees about vertex B. Then give the coordinates of the vertices for triangle A prime, B prime, C prime. Okay, let's go back to the first thing the problem said. Graph the figure. All right, let's go ahead and put A, B, and C where they belong. A would be 2, 1, so I go right 2, up 1. That's where A should be. B is 1, negative 1, so I go right 1, down 1. There's B. And then C would be 4, -1, so 4 to the right from the origin, and then down 1. There's point C, all right. And then I need to graph that figure. That figure is a triangle, right? That's what it said. Of course, I should already know that. And let's quickly go ahead, connect the dots, and boom, there's your triangle. All right, so the figure, it has been graphed. Now, we need to graph the image after a clockwise rotation of 90 degrees. Okay, so that's important information right there. Clockwise rotation of 90 degrees. And what's my point of rotation? What's my center of rotation? Vertex B. So vertex B is going to stay where it was. So B will be the same as B prime. It's not moving. All right? That's the center of rotation as it told me. And it needs to be a clockwise rotation of 90 degrees. So remember what the first page taught you. What used to go up will now go to the right. What used to go right will now go down, and so on and so on. That's how a 90-degree rotation, clockwise rotation, will work. So how do I apply that? Well, from getting from point B to point A, let me put this in green, I used to have to go 2 spaces up and 1 space to the right. But when I rotate that 90 degrees, what used to go up will now go right. What used to go right will now go down. And so let me go ahead and show you how that's going to work here. That's what I need to do. Instead of going up 2 and right 1, I'm going to go right 2 and down 1. And that is where point A prime is going to be located. Now let me go ahead and delete this green thing I drew. All right, let's apply this to C prime. What did I used to have to do to get from B to C? I went 3 spaces to the right. Does everybody see that? From B to C, 3 spaces to the right from B to C. Well, let's apply what I taught you on the first page. What used to go to the right will now go down. So instead of going 3 spaces to the right from B to C, I'm going to go 3 spaces down from B prime to C prime, and that is where C prime will be located. Then I have to connect the dots, draw my triangle for A prime, B prime, C prime. Am I done with the directions of this problem? Nope, one more sentence. Give the coordinates, that's what it says right here. Give the coordinates of the vertices for A prime, B prime, C prime. So what do we have? Well, B prime is the same as B, right? So that's still going to be 1, -1. A prime is now what? I went from the origin. That's where you got to count to get your coordinates. From the origin, I'd have to go right 3, down 2. So that's 3, -2. I already said B prime is the same as B. And then what about C prime? From the origin, right 1, down, what is that? 1, 2, 3, 4. So that's 1, -4. And there you go. There are your 3 coordinates for the vertices of the image, which is the new figure after the rotation, A prime, B prime, C prime. Now, anytime I explain something, if you're like, what? Say that again, hit rewind on your video, go back. If you have to hear me say things more than once, that's the advantage to having this pre-recorded on a video. You can go back and hear something explained more than once to help you understand. All right. Moving on, let's go to the next page. Rotating a figure about the origin. Now, what does that mean? Well, follow along in the box. Rotating a figure about the origin means we're going to use 0, 0, which is the origin, as the center of rotation. So, I've given you 3 diagrams here with the original triangle drawn in blue, and then where that triangle would be if we rotate it about the origin. Again, that's the key here. About the origin means the origin, which is 0, 0, that's your center of rotation, instead of being some point on the triangle like we had on the previous problem. So, the same things apply as we learned before. For understanding a 90-degree rotation, I used to have to go to the right and up to get to this point here. Well, now, instead of going right and up, I will go down and right. That's how a 90-degree rotation works. Here, you don't believe me? I'll go ahead and rotate it 90 degrees. Boom, you can see that. And that's how I get from the origin to that first point here on the corner right there of that triangle. And that's the idea for 90-degree rotations. You would do that to figure out where the other points go. 180-degree rotations, as I taught you before, these are the easier ones for kids to understand. Instead of going right and up, you go everything opposite, so it'd be left and down. All right, so that one's pretty easy for kids to understand. The trickiest might be the 270-degree rotation. However, I want to remind you that, let me go back and draw what I drew earlier in red, going right one, up one. A 270-degree clockwise rotation is the same as going counterclockwise just 90 degrees. All right, and so that's another way of thinking of these kind of problems. If you ever have a 270-degree rotation, it might be easier to just go the other way. So in this case, instead of clockwise, counterclockwise, and then just go 90 degrees, and they will be the same thing as I just showed you right there on that example here on the right. Okay, here's another typed up example for you in your guided notes. Follow along as I try to explain this to you out loud. I'll read it out loud. You can follow along. A triangle has vertices A, B, C. You can read what they are. Graph the triangle and its image after a rotation of 270 degrees clockwise about the origin. Then give the coordinates of the vertices for triangles A prime, B prime, and C prime. All right. So step one, graph the figure. This is not hard as long as you remember how to graph ordered pairs. You count from the origin and boom, A, B, C, there it is in blue. Now, that's the first thing. Graph the triangle. We did. Boom. Now, the second thing, we got to graph the image. And remember, image means the new figure after we've had the rotation. So what's our rotation this time? 270 degrees clockwise. And like I've been telling you on this page, this is where the center of rotation is the origin. So we need to count from the origin, you know, how many spaces right or left, up or down to get from the origin to each point. And then we're going to rotate that 270 degrees clockwise. Now, I just told you a minute ago, 270 degrees is the trickiest one to do. So look what I wrote for you here to help you out. 270 degrees clockwise rotation is the same as 90 degrees counterclockwise. So that's honestly what I would probably do. Since vertex C, forgive me, I skipped the sentence. Since vertex C is the closest to the origin, let's go ahead and start with C. All right. So how did I originally get from the origin to point C? Well, I went 2 to the right and 1 down. And you can see I have this typed up for you. Count how to get from the origin to point C, which is 2 spaces to the right, 1 space down, just like I drew for you over here in red. Now, we have to rotate that 270 degrees clockwise, which is the same as 90 degrees counterclockwise. Here, let me prove to you. Here's me rotating it 270 degrees clockwise. There it is. Whoops, a little off. There we go. That is the exact same thing as going 90 degrees counterclockwise. So that's probably the easier way of doing this. And that's how much I have to count from the origin to get to the new point C, which is called C prime. So instead of going to the right and down, I go up and right, because that's how a 270 degree clockwise or 90 degree counterclockwise rotation will work. And so, continue on. So that's how we're going to graph C prime. All right. And what I have typed up for you is what I just showed you over here in red on the graph, that you're going to go 2 spaces up and 1 space to the right. Notice how the coordinates of C were 2, -1, and the coordinates of C prime are 1, 2. So do you see how the numbers still show up? Now, obviously, instead of -1, it's +1, but the absolute value of the numbers are the same. So you need to keep that in mind with 90 degree rotations and 270 degree rotations, and honestly also 180 degree rotations. You're still going to have the same number of spaces. It's just that it's going to be different directions once you rotate it. All right, step 3, continuing on. Now we're going to graph A prime and B prime. So for example, to go from the origin to B, we used to have to go 4 spaces to the right and 4 spaces down. Here, I'll prove that to you. 4 spaces to the right, 4 spaces down to get from the origin to point B. But now I have to rotate that 270 degrees clockwise, which is the same as 90 degrees counterclockwise, which is what I'm going to do because that's the easier way. So instead of going right and then down, we're going to go up and then to the right. And that's where B prime will then be located. And then the same idea with point A. Instead of going to the right and then, what is this, 5 spaces down, I'm going to go to up and 5 spaces to the right. The triangle should look congruent. Remember, that's one of the first things I taught you on these guided notes. The triangles will still be congruent, still same size, still same shape. It's just that they're obviously going to be rotated. Last part, connect the vertices to form A prime, B prime, C prime to form the triangle. Then step 4, since the directions, please don't forget to reread the directions. Make sure I've always made sure you did the directions correctly before moving on to the next problem. It says give the coordinates of the vertices for the new triangle. So boom, I figured out what they are. Count from the origin to A prime, B prime, C prime, and that's how I got these coordinates. All right, if you didn't like the 270 degree rotation, because that's a little tricky, here's good news. Problem number 6, look what we have. A 180 degree rotation. See, Underkoffler's trying to be a little nice to you here. This one is the easy one to do in retrospect compared to all the other types of rotations that we're going to be looking at today. 180 degrees is the nicest. All right, if you think you can do this problem on your own, great. I would love for you to do this on your own. Obviously, I can't control that. So if you're going to do this on your own, hit pause. If not, and you want to hear my explanation right away, fine. Let it continue playing. But once you get to 7 and 8, I'm definitely going to want you to do those on your own. All right, so we have a parallelogram with the vertices. The first part of the second sentence for the direction says graph the parallelogram. So let's do that right now. A is -3, -1, so left 3, down 1. Boom. B is 1, -2, so right 1, down 2. C is -1, -4, so I'm going left 1, down 4. And then D is -5, -3, so we're going left 5 and then down 3. Hopefully I counted all this correctly. And this should, according to the wording, should be a parallelogram. So let's see. Yep, it looks, yep, there you go. It is a parallelogram, a little tilted parallelogram, but it's a parallelogram. All right, so that's the first part of the second sentence's directions. Graph the parallelogram, great. And its image. All right, image means the new figure. After a rotation of 180 degrees clockwise, okay. Do you remember how 180 degrees clockwise works? Everything goes in the opposite direction. That's how it works. And the point of rotation, again, just like we've been doing so far, is the origin. So we have to count from the origin and then do everything in the opposite direction. So to get from A, we used to go left, then down. Reverse that now, because 180 degrees just goes everything in the opposite direction. Instead of going left and down, we're going to go right. How many spaces is that? 3. And then up. So again, instead of left and down, right and up. Everything goes in the opposite direction when you do a 180 degree rotation. How about B? Instead of going right and down, we're going to go left and up. For C, instead of going left 1 and then down 4, we're going to go right 1 and up 4. And then how about D? Instead of going left 5 and down 3, we're going to go right 5. Is that 5? Yeah. And up 3. There we go. Good enough. And let's draw the image, which is a parallelogram again. And notice, it is congruent to the original parallelogram. In fact, it looks exactly the same, which is, you know, when a parallelogram is already having 2 pairs of congruent sides, then it's still going to have 2 pairs of congruent sides and look kind of like they did before, just obviously at a different place since it's now been rotated 180 degrees. All right, are we done? No. Last sentence. Give the coordinates of the vertices for A prime, B prime, C prime. So what is A prime? Right 3, up 1. So that's positive 3, positive 1. B, I went left 1, up 2. So that's negative 1, positive 2. C, I went right 1, up 4. So those are both positives. And D, I went right 5, up 3. Those are also both positives. And there you go. Don't forget your ordered pairs, x before y. And there are the coordinates for the vertices of A prime, B prime, C prime, D prime. Okay, problem 7 and 8. The directions are a little simpler than the past few. The original triangle is already graphed for you. Yay, you're all happy, less for you to do. And it's not going to ask you this time for any coordinates. The only thing it tells you to do on number 7 is to graph the triangle after a 90 degrees clockwise rotation about the origin. Number 8 says to graph the triangle after a 180 degrees rotation about the origin. I definitely want you to do these problems on your own. So hit pause on the video, then hit play whenever you're ready to see how you did. All right, I hope you have done these problems on your own. Otherwise, you better hit pause now, because I'm now going to reveal where these new triangles should be and how they should look. So, the 90-degree clockwise rotation, that's always the trickiest one for students to figure out. I would go back to the very first page where I taught you that what used to go, up was now going to go right. What used to go right will now go down. What used to go left will now go up. So here's what I mean. I know I've been explaining this over and over again. I used to have to go left and up to get from the origin to this first closest point here on this triangle. But if I rotate that 90 degrees clockwise, I'm now, as you can see, going to go up and then to the right. And so, hopefully you did that with all 3 vertices of the triangle. And let me go ahead and delete this little drawing I did. There we go. That is where the triangle should have been after a 90 degrees clockwise rotation. Make sure, instead of being 1 space up from the x-axis, that your triangle is 1 space to the right of the y-axis. All right, please double check that you have these points where they belong. Every year I have some kids who have the triangle too far down or too far to the right, so please double check that very carefully. All right, problem number 8. This is the one kids usually like, because 180 degrees, as I've said over and over again, it just goes in the opposite direction from how it used to. So instead of going left and then up, you're going to go right and then down. And that will put you over here in quadrant 4. There's the image after 180 degrees rotation about the origin. All right, the very last thing we're going to look at on these guided notes is something called rotational symmetry. Since we've been talking about rotations, this is the last piece we need to talk about, rotational symmetry. Follow along. It says, if a figure can be rotated less than 360 degrees about its center, so the image matches the original figure, then the figure has what we call rotational symmetry. So here's what I mean. Let's take, for example, this snowflake. The center of the snowflake, obviously, is here. I can rotate this, and it ends up looking the same. Now, how many times can I do that? Well, I actually tried to count that for you up here on this little think statement. It's actually 6 times that I can rotate this around. 1, 2, 3, whoops, almost too far. 4, 5, 6, and I'm back to where I started. There you go. So that proves to you that this can be rotated 6 different times so that the image matches the original figure. So this has rotational symmetry. Now, what I can do, first of all, forgive me for not even reading the directions, my bad. It says determine if the shape has rotational symmetry. So yes, it does. We just proved it. If so, describe the angle of rotation. Now, how do we do that? Very simple. Remember how we could rotate this 6 different times and have it still match the original figure before we're back to where we started? So what I do is I just take 360 degrees, because 360 degrees is going the whole way around, which puts you back at where you started. I take that value and I divide by how many points that I had that I could rotate it to make it the same. So that was 6 times. No coincidence, this snowflake has 6 points. A little shortcut there for how you could also figure out that you could rotate it 6 different ways for it to still be the same. So take 360 divided by 6, and that will give you the angle, oh, that's a typo, angle of rotation, not angle or rotation, my bad. Angle of rotation. Please fix that typo. Man, I tried to proofread this before I sent this out. Oh, anyway, angle of rotation is 60 degrees. All right. Now that I've done number 9 with you and explained it, please do 10 and 11 on your own. So hit pause on the video, then hit play when you're ready to see if you got it right. Okay, I hope you've done 10 and 11 on your own. Problem number 10. We have this type of looking flower or whatever this is. It appears that I could rotate this 3 ways for it to stay the same. No coincidence, there's 3 petals on this, so a little hint there. And this definitely then has rotational symmetry. What's the angle of rotation? Well, since I could rotate it 3 times and it still stayed the same during each of those 3 times, then I take 360 degrees divided by 3, and that gives me an angle rotation of 120 degrees. Problem number 11, I have a star, a 5-point star. Does this have rotational symmetry? Absolutely it does. I could rotate it, no shocker, 5 times, and the star would be exactly the same as it was to begin with. So therefore I say yes, it has rotational symmetry. Take 360 divided by 5, and that gives you the angle of rotation is 72 degrees. And that's the end of the guided notes on rotations on the coordinate plane. Thanks for following along. We'll see you next time.